Okay. So this is section 2.3. It begins on page 84. And the name of it is Postulates and Diagrams. You've seen some of the diagrams before. We'll see them again in this section. But the word postulate, anybody know what that is? A postulate is a statement that we accept without proof. Because we have to have some place to start. Like the foundation of a house. You can't live in the foundation. You've got to have one to live there, right? There's something at the bottom that we begin with, and they are called postulates. And there are, ones we're going to study today anyway, there are 7 of them. On page 84, they are called postulate 2.1, 2.2, 2.3, and so forth, up to 2.7. And you may refer to them that way if you wish to in your exercises. Like you say, it'll say, what is true about this, explain, and you would say, because of postulate 2.4, this is true. Something like that. Okay, so you may refer to them that way. Now we need to discuss the details of them, the things we accept without proof, and that means that they are so simple they're hardly worth talking or writing anything about, but you'll see they can be kind of involved and kind of weird because of the way they're stated. So just stay with me, I'll try to talk you through them. The first one is about lines and points, the first two. You see how they've delineated some of them with lines as you go through, you see those horizontal lines? The first two are related to each other. And here's what the first one says. It's called the 2-point postulate. It says, through any 2 points, there exists exactly one line. And I'm talking any 2 points. I don't care if they're in space, or on the board, or on your paper, or in your book. Most of the time we draw them on planes because that's how we do things in school. But I could say that we have this point at the end of this pen, and we have this point down here. Can you imagine that there's only one line that goes through them? Is there any other? There's not more than one, right? Is there one? Yes. What if I move this point out here? Is there one that goes between this one and this one? Yeah, and it's different from this one, right? So what we say is 2 points determine a line. Usually we draw those 2 points on a grid or on a board or on your paper. Now look at the other one so you can compare them. Section 2, part 2.2 says, this is called the line point postulate. And it says, a line, if you have it, that's what I'm saying, without a line, contains at least 2 points. That's ridiculous. Any line that you talk about contains an infinite number of points. But it contains at least 2, right? So that one's kind of weird and kind of dumb and kind of strange. The fact that we have 2 points make a single line, that's kind of important. But the fact that if you got a line already, and then there must be 2 points on it. Can you see that those are converses of each other? Because we could make an if-then statement out of the first one, which would say, if I have 2 points, then there is a line that goes through them. If-then, right? On the converse of that, let me go ahead and write that down. If I have 2 points, if 2 points, I'm just going to say, anywhere, I don't care where they are, in space, any place. If 2 points, then one line. So the converse of that would be, if one line, then 2 points, but we're saying then at least 2 points because we know there's more. So this one's quite useful. This one's kind of weird because it's obvious and ridiculous. So it's biconditional because the statement that it's conversable true. But they're calling them postulate 1 and postulate 2, 1 and 2, 2. So that has to do about 2 points in a line, or a line has at least 2 points. You got to figure out which one you've got and what you can conclude from it. We'll do some exercises in that. Look at section 2.2 or part 2.2. Or excuse me, 2.3. It's kind of by itself. And here's what it says. So you look at the diagram while I read this to you. It says, if 2 lines intersect, then their intersection is exactly 1 point. Not more than 1, not less than 1, exactly 1. That makes good sense, I would think. You got 2 lines. Remember, lines are straight. You can't have a bendy line do something like this. You can't have a line here and then have another line come in there and come back and do that. That's not a line. If you have 2 lines which cross, they will cross in exactly 1 point. All lines have to cross. We have ones like this that will never cross. Let's pretend that's parallel. Those never cross, so there's not guaranteed to be a point of intersection. We're saying if they cross, then the place they cross is exactly one point. I want to show you something else, which will come up in just a minute. I'll talk about it again in a minute. It doesn't even, lines don't even have to be parallel to not cross. These lines don't cross. No, they're not parallel. So they have to cross. And if they do, their crossing is one point. That's what that postulate is saying. Okay? The next two, the 3-point postulate and the plane point postulate, are very much like the first two, only they have to do with planes instead of lines. And the first one says, through any 3 non-collinear points, there exists exactly one plane. We talked about this the other day, but I'm going to bring it up again. If we've got the plane of this, find something that's stiff like this. If we've got a plane like the back of this right here, and we've got 3 points that are non-collinear like this, not on the same line. I don't care if one's sticking up above the other or anything like that. We can put a plane on them, and those 3 points will determine that plane. Because as soon as we lift it off of one of them, I guess I better go over here. As soon as we lift it off of one of these 3 points, I don't know if you can see those 3 points there. Now it's no longer the plane that was determined by them. Tip it off of that one or tip it off of that one. It's no longer. If it contains all 3 of those points, then these 3 non-collinear points determine that plane that sits on. That's why a 3-legged stool never wobbles. Think about that. 3-legged stools never wobble. 4-legged stools do all the time. If these are collinear, we talked about this the other day too. And this is hard to do. If these things are all in the same line, like that, you can't have a plane that's determined because it'll fall. That plane is determined by those 3. So this, and this. So 3 collinear points cannot determine a plane. They have to be non-collinear to determine a single plane. Got that? Yeah? So that's what that first one's saying. And the next one says, the opposite of it, or the converse of it, says a plane contains at least 3 non-collinear points. So we do the if then on that, just like we did with the points on the points in the line. Now we're going to do points in a plane. If there are 3 non-collinear points someplace, then there is one plane determined by them. And the converse, just like this line one here says, if one plane, we got a plane that we're considering, then on that plane, there's at least 3 non-collinear points. This one, again, is an obvious thing. A plane has billions of points on it, too many to count infinitely. But there's at least 3. And those 3 are non-collinear. Okay. Moving ahead further, we got the next one. It's all by itself, and it says the plane line postulate. Now we're going to start mixing them together, planes and lines, in the same kind of diagram. And it says, if 2 points lie in a plane, then there's a line containing them in that plane. The line is also in the plane, is what they're saying. So if I have 2 points in a plane, like the plane of this board, not something out here at the end of this marker, but this point and this point, then the line that contains them, we've already agreed there's a single line that contains them, but that line is also in the plane. Kind of a duh. I agree. Okay. And the last one says, if 2 planes intersect, then their intersection is a line. Here's the best example of that. It would be your book. Here's a plane that my hand's holding right here, and here's a plane right here. And where do they intersect? It's called the gutter. It's the gutter of the pages. That's a single line. There's a straight line where they meet. Yeah? Okay. And I think I've had this discussion with you before, but I'm going to bring it up again. If you have 2 lines which cross, and lines are one-dimensional, aren't they? All they have is length. If you have 2 lines that cross, they cross in a point. What's the dimension? How many dimensions is a point? See, it has neither length, width, or height. It's just a location. So one-dimensional things, when they cross in a 0-dimensional intersection. Two-dimensional things, like your hands, when they cross, these are two-dimensional, cross in a single line, which is one-dimensional. What do you suppose that two three-dimensional things that cross in? A two-dimensional plane. Think about bubbles. You have bubbles up there, they're three-dimensional. They're spheres. And when they hit each other and stick, that thing in the middle is a circle, which is a plane. Two-dimensional. So every time two things cross that have the same dimension, they cross in something that is one dimension less. Okay? All right. So you're probably going to want to return to this page a lot and read them carefully to make sure that you have what you think you have when you name the postulate that does these things. I want you to look at example 1 because this is where it can get a bit confusing. Can be. Example 1 says, identify a postulate using the diagram. Notice what they say. They say, if this situation, then this one. So we've got two lines that are crossing, and then notice that they've highlighted the crossing points. So which one of those does that? 2.3. 2.3, good. And look at the next one. It says, if crossing planes, that's what you're seeing there in the picture. If crossing planes, then, and notice what they highlighted was the line. That's the postulate 2.7. Good for you guys. Okay, look at example 2. Use the diagram to write examples of the plane point postulate and the plane line postulate. That means we've got to focus on those two and see if we can use this diagram to write examples. So the first one says the plane point postulate. Where's that? Okay, we'll find it. Plane point postulate is 2.5, right? And it says if a plane, if we wrote it in that form, say if we have a plane, then there's at least 3 non-collinear points. Do we have a plane?
Yes.
We've got 2 of them. Do you see any of them, or any 3 non-collinear points in one of them? Which ones?
B, A, and C.
Good. B, A, and C. And notice how the author writes it. He says plane P contains at least 3 non-collinear points, and they are A, B, and C. Okay? We're also supposed to use the plane line postulate. Where's the plane line postulate? Which one's that? 2.7? Okay. The plane line, oh no, that's the plane intersection. The plane line postulate says that there will be at least, if there's 2 points in a plane, then the line that contains them is in the plane. So do you see 2 points in a plane that have a line on them?
Yeah.
Which ones?
A, B.
Sorry? Plane P, and what's the line?
A, B.
N or BA. And so you would say, in plane P, line N, no. In plane P, B and A contain line N in the plane. Let's see how he says. Points A and B lie in plane P, so line N containing points A and B also lie in plane P. You might want to go back to the solutions and see how the author represents it. You're going to do a lot of writing again today. Which postulate applies to what? Turn page. All right, now, you can already see the sketch on this. I want you to cover it up with your hands. Don't look at the details. Cover up that sketch, because when you do your exercises, you're not going to have the solution in front of you. You're just going to have words. And from the words, you have to produce a picture that has all the things the words say and none of the things it doesn't. So you may not assume anything. You can only write or draw what's written.
I need the following students to come to the office: Abigail Anderson, Kimball Anderson, Taylor Anderson, Dylan Ball, Lindsay Beasley, Stockton Birch, Taylor Brown, Caitlin Preston, Allie Christensen, Darren Cook, Sophia Doherty, Alan Bond, Ivan Harper, Shay Harrison, Tegan Harris, Brandon Little, Jordan Llewellyn, Tyler Mendoza, Nika Mead, Haley Robertson, Tyler Williams, Curtis Wise, Aubrey Evans, Taylor Madsen, Marisol Gonzalez, Sophie Crapo, Ammon Dye, Chauncey Jones, and Amberlyn Kinghorn.
If that's any of you, what you missed is your problem. You're going to have to watch the video to catch it. Here we go. Example 3 says we're going to, don't look at the sketch itself. We're going to have to take the words and make the sketch. Example 3. So here's what it says. Sketch a diagram showing line TV. So you should start that way. Draw yourself a line, TV, put a T and a V on it. Intersecting segment PQ Ooh, I gotta see where it's gonna intersect if it lands at TV or something. Intersecting segment PQ at point W. Oh. So I'm gonna have a segment which intersects this at Q. What's the name of it? TV? No.
No, it intersects at W.
So PQ,
Yeah,
that's the segment?
yeah, and it intersects at W.
Oh, W. Okay, so we've written down what we see in the words. Show that TW equals WV. Oh, in other words, they want us to mark it. So, so even if you had this crash and W was clear over here, you can still mark TW and WV with a couple of slashes, and even if they don't look anything alike, even if they don't look at all like they're equal, if you put the marks on them, we'll assume that they are. And that's what they mean, is to mark those two things equal. Okay? So that's the diagram you would produce from those words, and that's what you see in the book there. It's not quite the same, but it satisfies all the conditions. Everybody okay? All right. Now we're going to interpret a diagram. Before we do that though, look just before example 4. You see those strange looking perpendicular boxes they've got there? Mm-hmm. What they're saying is that line Q and AP intersect line T all together at that single point, and T is perpendicular to both lines. That's what they're trying to indicate, those strange looking boxes. That does not mean that AP. No, sorry. A is the plane. That does not mean that P and Q are perpendicular. It means that T is perpendicular to Q, but not necessarily that P and Q are perpendicular. You understand what I'm saying? And then we can have P and Q crossing on the plane like this, and have a line coming through that's perpendicular. Don't make any assumptions. Anyway, example 4 says, which of the following statements cannot be assumed from the diagram? So we're looking very closely at the diagram. What does the little red box in this case mean? It does mean 90 degrees, but what's at 90 degrees? The two planes are. The two planes are perpendicular when they cross. Okay? All right, so look at those things. Do you see any other markings that they have? Actual markings anywhere except for that red? I don't see anymore. So here's what we want to do is find the ones that cannot be assumed. Points A, B, and F are collinear. Can we assume that A, B, and F are collinear? Yep, so that one we can assume, so that's not one. Points E, B, and D are collinear. E, B, and D. Can we assume those are collinear?
No.
No, they might be. Can't assume it. Can't assume it, so that's one that we can't assume. How about AB perpendicular to plane S? Line AB is perpendicular to plane S. Can we assume that?
Yes.
Yes, because AB is in T and T is perpendicular to S. How about CD? Y'all find CD? Is it perpendicular to plane T?
No, because the season.
We cannot assume that. Or can we?
But it goes like.
Yeah, hang on there. Yeah, I'm thinking we might be able to. What do we say? CD. We all see CD, and it's lying in plane S. Is it perpendicular to plane T? I would say it is, because S is perpendicular to T. So that's something we can assume. That's a strange one.
Isn't the C like on the lines like B and T too?
It is, but CD continues back there with that bottom one. CD, the line CD is in plane S. And since S is perpendicular to T, any line that's in S is going to be perpendicular to plane T. Okay? And the last one says AF. Y'all find AF? AF intersects BC at B.
Yes.
Yep, we can assume that. So that means that's not one we're going to check. It's not one that we choose because we're trying to find things that we can't assume. We're okay? That was rough. Okay, we are at the exercises, and there are 23 of them, and I will give you that assignment before I turn off the video. You're playing with the postulates, making sure you understand which postulate. You can refer to them by the numbers. You'll be doing some drawings based on words like this, and you'll be looking at some drawings and trying to draw conclusions or not. You play with some stuff. Here's the assignment. Are you ready? I want you to do number 1, 3, 4, 5, and 7. 9 through 22. 24 to 26. And 29.